Okay, so it seems we are online. So hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you a simulation of centrifugal fan. There will be a lot of information shared with you today. We will show you how to simulate step by step a centrifugal fan, how to do the setup and of CFD simulation, how to run it, and how to evaluate it. And there are also a lot of other aspects to evaluate and what to do about the virtual prototyping of centrifugal fans. So let's get to it. So the webinar will take about 1 hour. And we will do our best. In the first part, I will make a very quick introduction to what's on the table, and in the second part, my colleague Radek Maca will show you how to really actually do the things, how to do the setup, how to think, what to do. And in the last part, there will be a Q&A session which will be dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. There is a special window in the application, so you can ask your questions, and you can be sure that all the questions will be answered. Those most representative questions will be answered right away in the webinar. The rest will be answered later via email, but you can be sure all the questions will be answered. And yes, a lot of people ask if the recording will be later available. So yes, the recording of this webinar will be later available. So you can view it. You can watch it later, and that means you can just follow the principles and think about what it is that you need, what would you like to have in your engineering process, and let us know, and we'll do our best to support you. And yeah, let's get to the rest later. So I will slowly start. I will be very quick in the beginning. I'll just comment with just one sentence every slide, and then we will jump right into the action and show you a real hands-on experience and a real hands-on session, which Radek is best at. Okay, so I'll start with quickly the company name is CFD Support. We are a business which is located in Prague, Czech Republic, and our main or our primary business is simulation software. It's primarily CFD simulation software, FEA and FSI, which is connected with CFD, of course. It's also the optimization and newly the acoustics. So there are a couple of modules that can be used or not used. It's always up to the user. And our flagship product is a simulation environment called TCAE, which is a system of simulation modules, of software modules that are based on open source. And we have taken it and redesigned it to be ready for the industry, and it's very successful because it has benefits of open source as well as benefits of commercial code. So it will be our pleasure to show you. It definitely makes a lot of sense to use it, and it has very high added value. So there are a couple of modules, part of it. They are like standalone tools. So especially there is meshing module, CFD module, FEA module for structural analysis, the acoustics module that can evaluate the sound and noise of the flow. And there's also the optimization module, which can run large loops to evaluate a lot of design candidates, etc. There's and that's another story. We are also working on a special module which will take care of writing data down and into the special databases, and also machine learning modules will later take care of it, because it seems that in the future we will be a little bit less simulating and a little bit more like quickly designing things based on the data we have simulated before, because it seems that we can take lessons from what has been simulated in the past. Okay, so that's the software. It's extremely flexible. So you can play a puzzle. You can use whatever module you like and combine it with in-house codes, commercial codes, other open source tools, with ready-made solutions or scripted, and it's endless. It's infinitely flexible according to your purposes. I guess you know that every engineering office workflow is a little bit different, or actually very different, and it's always yeah, another story in every engineering office. So you can play puzzle, and definitely TCAE is definitely ready to fit an existing workflow and get into it and work. Okay, TCAE is unlimited. Yeah, it's there are no limitations on number of users, jobs, or cores. There are no limitations on hardware installations, so you can get lifetime license. It's very useful in these terms. It's focused and accurate, but I'm not gonna talk too much about it. It's automated, and for this reason, it's extremely effective. The new version, the latest version, 22.10, we released at the end of the last year, and is brand new and again very efficient. And yep, TCA consists of a lot of open source pieces, which were like improved to be ready for the professional usage out there in the industry. We've spent enormous time and effort to deliver this package. We've spent more than 40 man-years in the team development, code development, and testing, and creating special tutorials to make tests and benchmark things. So a lot of work has been spent in the past, and that's the solution is so unique. We are already working on a new version. Of course, there will be a lot of new things. We hope that we will release it in spring, and then another version in autumn this year. So let's see. But anyway, I'll get back to the centrifugal fan, which is today's topic. So today we would like to show you a little bit how to design, but the design is special discipline, which is different in every engineering office. So you can use some ready-made professional tools, or you can use some scripts, or you can use your own tables, or it's very large topic itself, the design. So we can show you a way, or we can advise you if you come back later. So there's the design. Then there's when the design helps you to create the surface model, which is the input for the simulation, and the simulation then is relatively easy to set up and run and evaluate. The world is so complicated because, for example, the optimization is possible. So you can play with all the parameters regarding the topology of the model, or simulation parameters, or pretty anything. So it's extremely flexible in these terms. And yeah, so that's also an option. So we'll be happy to help with this. And that leads me to the practical part, which we will ask my colleague Radek if he's together with us and ready to take over the presentation. So Radek, knock knock, are you with us?
Yes, hello Lubos, and hello to everybody who's watching us.
Great, Radek.
Yeah, I'm ready. Yes.
Okay, good. So I'm going to hand over the presentation to you. So I will tell you.
So
yes, now we can see. We can see it. Yep.
Okay, great. Thank you, Lubos, for the introduction, and hello to everyone again who is watching. So today, in my part, I will show you how to set up this simulation workflow for centrifugal fan. All the details about this particular case you can find on our web pages. If you go to the case studies, you will find this particular study. and you can open it and you can read it into more detail and for example try by your own, because this tutorial case can be downloaded, and if you are new in TCA you can ask for a trial license and everything try by your own. So today we will be playing with this particular case. As Luboš already pointed, the surface geometry was created in our, let's say, in-house script connected to the Salome software, which basically, based on the bunch of parameters, it will create the final shape of the centrifugal fan and creates all necessary surfaces in STL format or the solid for the FEA analysis. And basically I will start with the output of this script or this Salome program, Salome script. So this can be alternated by any other tool which creates the surface STLs, which then can be used for setting up CFD simulation, FEA simulation, and then everything put into the optimization loop, for example. So let me directly jump into it. So here, let's say in my working directory here, I have some preset cases, but I will just take the parametric model. Basically, this tutorial you can download it from our web pages and use it by your own, as I already mentioned. But I will just take this, let's say, this geometry builder, yeah, which includes the script, which can be run in Salome, and it will give us the set of STLs which we use for creating the computational domain, etc. So let me just copy it. So let's copy, and I will go to here, and I will create a new folder. So webinar project, for example. So this will be the plain folder, and I will copy this geometry builder here. So what I need as the first step, I definitely need the inputs. So usually for TCFD, for CFD simulation, it is a geometry which is the most important input. So I will be using this STL to setting up the mesh for the computation. Then I will set the CFD simulation. Then I will put everything into the optimization loop. And if there will be some spare time, I will show you how to, for example, also set the FEA analysis, which can be also connect or put into this optimization loop. All right, so here's my webinar project, and I will go and I will directly open the TCA. So I will be using the latest, so 22.10 version of TCA, and let's go for it. So here in this new version, I have several options how to create a new project. So I will start with creating an empty project in this case, but you can also create a new project based on an existing one. So it will just load the preset parameters, or you can load it from the previous version or with a specific configuration file, which is in the format as in the previous versions. So let me start with really the empty project. All right, so as you can see, we have 5 modules which we can use for our analysis. So today we will definitely use the TMesh for setting the mesh for the computation, both for CFD or FEA. And then we set up the CFD simulation, then we put it into the optimization loop. So we preset the optimization. Then possibly I will quickly show how to easily incorporate the finite element analysis into this loop. And maybe in the next webinar we will introduce in more detail some tutorial for the acoustic analysis, which can be also applied for the centrifugal impellers and so on. But this will be not the task for today, but the acoustics can be a part of your workflow with TCAE in this version. too. So let's start with the TMesh module. So I will activate the TMesh module. Then we will see here in the pipeline browser the new item TMesh, using which we can preset the simulation. So let's start with it. So the mesh output, we will start with the CFD, but when you would like to also use or to simulate the finite element analysis, we can create both meshes or simulation domains, both for CFD and FEA analysis. Here is an important button, let's say, or checkbox, use external geometries. So this, because in this new version, you can import all the geometries into the project. So then it lives within the projects and you don't use any external data which lies outside the project. But when you would like to set up the optimization, you need to use the external geometry, because usually the external tool, like in this case Salome or any other CAD, which creates for you the STL surfaces or STL geometries, you would like to need to store them somewhere outside, because every optimization loop, it recreates the STLs. So the TCFD or TMesh would like to take the STLs every time from the external path from the project. So we need to use the external geometries. This check external timestamps, it's not directly applicable for the optimization, but if you use the external geometries and you are working with the project, but then you change the STLs, then TCA automatically checks if the STLs are modified or not, and if they are modified, then we'll recompute the current project simulation or whatever. So I don't want to have it here in the optimization, because each optimization loop, it will recreate for me the STL, so it will be up to date all the time for each optimization loop. Scale factor, it means just what are the input units. And now let's go for the optimization, for the setting up the simulation domain. So as I already pointed, so we have bunch of STLs. In this case, we have 3 domains. We will use 3 domains, one suction part, then the impeller part or rotor part, and the spiral part. So here I will set 3 components. So usually we use components to distinguish between what are the rotating rotor parts, rotating parts, stator parts, or in multiphysics, the region with different physics, for example, for let's say some different applications. What I would like to also need, because it's turbomachinery case, so I would like to see some turbomachinery specific parameters when defining the mesh. And let's go for it. So component 1, it will be the suction part, so I can name it as a suction. Reference frame is static, which brings me here to the rotation reference frames. Here you define the rotor axis and origin of the rotation axis. Yeah, so in this case we have the rotation axis point to the y direction, and the same we set for the rotating one. So always we need to have one static frame and one rotating frame. So here the first suction part, which is just the inlet pipe, will be the static part, and now I will select the directory with the external geometry. So I will locate my working directory, which is here. So my webinar project, into the geometry builder. So in any loop of the regeneration of the geometry, the geometry builder will give me new STLs directly here into this STL directory. So I will load this STL directory, and now here I will put the STLs which define the input for the suction part. So here we have the suction. So suction will be the inlet, and suction wall will be the rigid wall. So I will set it as a wall. So anytime you see when you select an STL which will be used for meshing, then it will appear in my render view. And the last one I I would need the interface between the rotor part and the suction part. So we have nicely. So anytime, it's always clever to have a good naming to to know which part belongs to which component. So here for the component connection, there is specific type. So if this is outlet, so then there is outlet interface. So now we have nice component defined. So then maybe we will set other parameters, but first I will define all the components, surfaces, and then we will define the particular parameters. So for component 2, which will be the rotor or impeller, the reference frame is rotating. Again, I will select the same directory, and now I will choose all the STL which defines the impeller part. So here we have impeller. There are specific type for the walls, which for this turbo machinery specific application we have blades, hub, and shroud. So it's clever to assign a proper meaning to them, because then TCA internally can automatically assign the blade to rotating parts, hub shrouds to some, for example, turbo unwrap visualization tools, and so on. So let's start with this. So blade leading edge, we have blade pressure side, blade suction side, blade trailing edge. So this is the, let's say, main part for the impeller blades. Then we have impeller hub, we have impeller shroud, you can see, and impeller solid can be used for the finite element analysis, so it's not for the CFD. And definitely then we have the interfaces. So interface impeller to spiral, so it's outlet from the impeller, so we should assign outlet interface, and the same for the inlet, so inlet from the suction. So this will be the inlet interface. So it seems that all the boundaries are defined, so that we have nicely closed waterproof domain to be meshed. Then maybe I would check which this reference frame, it means if the given part is physically rotating. So all the parts are rotating here, and for the interfaces, it doesn't matter what is set there, because it knows that it's not a rigid wall. So internally TCA manager or TCA code knows how to treat these parts. And the last but not least, we will set the spiral part. So this is again the static reference frame. Again, we choose the same STL directory, and now we assign all the parts. So for this part, we have this spiral part, which is connected to the spiral domain. So we have part of the solid of the rotor, which belongs to the spiral domain. So we have spiral impeller hub, so we can set it as a hub. We have here impeller hub trailing edge, which means some detailed part of the domain, if you can see here. So if you double click, you can see that, yeah, this is the part of the solid which is connected to the outlet of the rotor. So it's always clever to, if it's possible, it's not compulsory, but if you split this detailed part explicitly, then you have more options how to refine just these parts. So it's good for the meshing purposes to have these kind of splitting. Let's continue. So now we have shroud parts. So again, shroud leading edge, some kind of an assignment to the shroud, and again, these are some detailed parts of the geometry. Yeah, here for example, trailing edge, and the leading edge, I think, is this edge of the solid. All right, then we have spiral outlet, so it's the physical outlet from the domain. We have spiral wall, which should be here. So this is the complete shape of the spiral. And just because there are some part missing. So I would like to see what is happening inside. So anytime you can go to the display part and set the opacity to your preferred value to see what is happening inside. So now let's go back to the setting up the component 3. And there is, I think for the spiral, it's all, I'm missing the interface from the impeller. So this is the inlet interface, which is this part. And I think I'm missing the part of this wall from the suction pipe or suction side. So I also need to import again the suction wall. So this I will import as standard wall. I mean this part, yeah, because it creates also the surface of the spiral part. All right, so this is it, and I also need to assign the proper reference frame because this part, for example, of the hub belongs to the stator static component. So I need to explicitly define that these surfaces are rotating. So then the solver prescribed the boundary, the velocity which correspond to the rotational movement of these parts. So this we can do for the surfaces which has this rotational symmetry. Yeah, then you assign the rotation within the stationary component. All right, so this we have assignment, and what we need to do other step is to connect the components. The connection is done again by the right click to the interface type. So here if I right click the outlet interface, so I need to connect to the correct component. So this is connected to the rotor and to the inlet interface, which is the interface suction impeller. So there is only one option. And similarly for the component 2, so the outlet interface is connected to the spiral. And then if the connection is proper, we can find the path from the first component to the third component. All right. So now we should set the meshing parameters. So I will get rid of this highlighted part, and let's go for setting up the other options. So find a proper parameter combination is always task for the iteration and for, let's say, for some investigation to get the nice accurate results. Because now we are in the webinar, I will try to create some standard parameters variation for the mesh, which gives us some rough mesh, but which can be applicable for the CFD simulation, because I would like to run it live. So I would need some reasonable amount of cells to get the simulation or the results quicker. So first parameter is the background mesh cell size, which is the, let's say, largest cell size for the computational mesh. If I would like, so usually I would like to use the cube cells, so or sites has the similar dimensions, and I think 4 centimeters for this case or something like okay. You can anytime you can show or highlight how this the proper proportional shape to the geometry. So this could be okay. Let's say we need to define the internal point because based on because the meshing is done by SnappyX Mesh, and it works that it creates such a, let's say, virtual cube in which the desired object to be meshed is placed. And now we have two options. We can mesh it from outside or from inside. So definitely here we need to mesh it from inside. So we need to put this internal point to the inside. So we can click here, show internal point with some visualization radius. So I will set it as 10 centimeters, for example, just for visualization. And now I need to put it into the inlet pipe. And that's it. And this we need to done for all components. So again, the the background mesh size 0.04. Okay, maybe for this, because this is the most important part. As you can see, the width of the impeller is much smaller than 2 cell size, let's say. So let's set it more finer, for example, for 2 centimeters. And internal point, again, I will put it somewhere inside the impeller. Okay, this should be fine. And for the last component, again, maybe I can set it again as a 4 centimeters, not 44. So in this way, and put the internal point inside. So somewhere, let's say here to the outlet side. Okay, this should be fine, I think. Yeah, it's inside. All right, so this was, let's say, this is the general parameter for the mesh refinement. And now maybe it's a good time to save the project if something happens. So I don't want to lose all what I have said up to now. So I will go to the webinar project, and here I will create, I don't know, for example, TCE. Okay, so now everything is stored, the project is created, and all the current setup is stored. So I'm not now much safer if anything happens. So let's go back and create quickly the refinement for each boundary. So let's say I will try to really create some quick and rough estimate for the mesh parameters. So let's say the inlet, I don't need to refine too much, and the wall, let's say I will refine to 1. So 1 level means that every cells near this surface will be split once. So instead of 1 cube, I will have there 8 cubes, basically. And the outlet interface, I will also refine, because the information comes from one side to the other side using usually arbitrary mesh interface. So finer mesh usually means more accurate interpolation. All right, then let's go for the second component. So here it will be more nicer or more complicated. So let's say for the inlet, where is it? Inlet interface is here. So I will set also level 1, and because my mesh is coarser here, so I will set here level 2 to be sure that the interface refined in a good way and the communication is accurate. Okay, then interface outlet interface to spiral. So this spiral part to the outlet is, let's say, more curved and is not so wide and big. So I prefer to set it, let's say, level of the refinement 2. Similarly for hub and shroud. So let's say hub and shroud, and pressure and suction side I will try to set to 1, and leading edge and trailing edge, which is this part, depends on the thick of the blades. I think it's something like 0.5 centimeter or 5 millimeters. So I would need at least, say, level 3 to have the size of the on the leading trailing edge to have something like 2.5 millimeters. It should be enough. So let me set level 3, and back to the impeller back to the spiral part. So again, here I have level background mesh size 4. On impeller I have 2. So interface impeller to spiral I will set to 3 to have the same refinement on this interface. Then I will go for hub, so to have the same refinement as on the rotor part, let's say. So I think for hub I set level 1. So here I will set level 2. And maybe for trailing edge, I will increase the level of refinement, and the same for the shroud part. But for the edges, I will set high level of refinement. Spiral outlet doesn't need to be refined. The spiral, maybe I will say 1 or 2. So 2 means that on the curved parts of the spiral wall, it will be the high level of refinement, and on the flat surfaces it will be the level 1. And on suction wall, okay, let's set the same. Okay, maybe I don't want to add the boundary layers because of the simplicity and to have the simulation quicker, but you can set as many boundary layer as you want, depending on what you need to achieve. Let's say the snap is some kind of, let's say, robust up to, let's say, 8 or 9 boundary layers. Usually we use up to 5, let's say, for industry application. But in this case, I don't want to add the boundary layer. For those who are more familiar with the SnapX mesh, you can find all the parameters here to be set, or even you can, for example, explicitly switch off the adding layer at all for each component. So for each component, you can have a specific combination of parameters. So let's say I will switch off adding layers to all the components, for example, but you can go through any, or you can change any SnapX mesh parameter. In the parallel run, my computer has 10 physical cores, so I will use all of them for the simulation. So let's give it a try if I set everything properly. So please keep finger crossed and let's go for it. So I have saved my current setup. So now I can click run all to see if the meshing is okay and if the mesh looks, let's say, okay for this webinar case. So it means if all the surfaces are well defined, there are no holes, no flaws in the mesh, and so on. So anytime any component is finished, a meshing of the component is finished, I can visualize the results. So here I can get rid of the input geometry and I can just look for the CFD mesh. Here I can visualize surface with edges. Yeah, so this looks fine for the simulation. Let's check the second component. Okay, rotor is also finished. So let's see. Okay, it's kind of rough, but for example, the edges, let's say, fine for our purposes. There are no weird shapes, no holes, no leakages, and so on. So it looks also good. And just wait for the spiral part. Anytime you can play, you can visualize, for example, what I would like to see what is inside. So I can create a clip or slice. So let's say create a clip, and which is perpendicular, let's say, to the x-axis and go through the origin. So let's click apply button. And again, now we can see, okay, what is happening inside. All right, so this way, and let's see if the last component is meshed perfect. So I can add the spiral part and visualize the third component. Okay, so I think it looks nice for the first try, but you know, I a little bit prepared for it, so I know what to say to have a nice results. All right, so this I am fine with the mesh, so I can activate the TCFD module and go for setting the CFD simulation. So let's do that. So now I will activate the TCFD module and quickly set simulation for the for my fun geometry. So again, I will just visualize the input CFD geometry. Okay, so go back to TCFD model and let's quickly set the CFD simulation. So here in the general, we have simulation type. Now we are simulating the fun or a fun. So the fun, and we will set the simulation type to fun, which gives us then some specific fun parameters and so on. So Now our simulation will be tailored to fan analysis. Here in the physics, I would like to have a steady state simulation. Even for the optimization, I really need to have a reasonable time for a single simulation, because, for example, if I would like to have hundreds of variation, then if my simulation take 1 day, I would need, for example, hundreds of days for the simulation. Yeah, so it must be cleverly chosen if the proportion about the between the accuracy and the time for the simulation and so on. Yeah, so it's at the end it's pretty complex thing to preset the nice and good optimization, which can be achieved within a reasonable period of time. Okay, so let's go for this. So I will use steady state simulation. I will simulate just one point, let's say some design point, and I would like to optimize the design point for this particular fan. Point of iteration for optimization, it is really important that each variation, each simulation will converge. Otherwise, if some does not converge and it will converge to some higher value of for the efficiency, it will broken the whole optimization loop, because then the optimization algorithm will decide that this non-converged case will be the best case, for example. So you must be really careful here. So a higher number is better for the accuracy here. A physical model, I will stick with the incompressible. I will stick with the standard air parameters. I don't need any multi-physics. For the turbulent model, I will stay with the K omega SST model. And in the rotational reference frame, I need to set the rotation. So here the direction of the rotation follows the right hand rule. So we have the axis which pointed to the y-axis. So if you point the thumb, your fingers then will choose the positive direction of the revolution, which is this, but we need to have this right rotation direction. So therefore we need to set minus, and this fan is designed to operate at 300,000 RPM. So let's set 300,000. Then go for the simulation. So solver, number of processors. Again, I will use the maximum on my computer. Numerical order. Usually we should go for the second, but this is my very first setup, so I will stick for the first. And if the simulation is okay, then I will go for the second to check if the second order scheme is still okay and robust and gives me good results. So just because this is the first try, I will stick with the first order scheme. Runtime evaluated quantities. So because even we are in the steady state optimization, the solution can oscillate basically for many reasons, but I would like to have really the averaged constant solution at the end. So I would like to average this iterative solution over the iteration time. So let's say if I set here 3000, so let's say I will set, for example, 200 for the averaging. And you can also set the average quantities, because you can have the instant values for pressure, velocity, and so on, but you can get also the averaged quantities when you are averaging the solution. And for example, for application to FEA analysis, I would like to map, for example, for fluid structure analysis, I would like to map the average quantity, not the particular one at the end of the simulation. So I would like to, for example, here I would like to save the average pressure for mapping on the FEA mesh if I would like to apply the FEA analysis. So efficiency probe. So basically define the places and parts from which the torque is evaluated, or the pressure differences from inlet and outlet and so on. So I will set it automatically. The inlet is inlet into the domain, outlet is outlet, and torque patches are all blade parts. But I would like to in the rotor region, but I would like to also, basically I would like to incorporate or rotating parts for torque evaluation. And then power evaluation. So I would like to check all rotating parts I want to include into the torque evaluation. Here, wheel diameter is for some specific coefficients evaluated for fun. So this impeller has 74 centimeters in diameter. So I will set this number. You can apply, for example, if you would like to see the forces acting on some specific part in your domain, you can set it here, or also you can watch some specific point, what is happening in a specific point in the domain, what is the pressure, what is the velocity, and so on. I don't need it. Convergent check is pretty important because I would like to set higher number of iteration. So if the simulation will be nice and the convergence is achieved much quicker, I would like to stop the simulation before the maximum iteration is reached. Usually I use the efficiency quantity because it includes several variables in it. So what I can set, so if the averaged efficiency quantity oscillates less than this relative value, so if the efficiency, for example, imagine if the efficiency is 100%, then this means that the tolerance is 0.1%. If it's 90%, it's 0.009% basically. So let's say I would like to say half, so 0.05 the tolerance in percent. So to be sure that the solution is converged, for example. Then we have these controls for the linear solvers, etc., for some bounding. So just only check if, for example, min and max pressure corresponds to your application, and that's it. And in the boundary condition, so at the inlet, so we will set the volumetric flow rate, and the design point for this fan is 10 cubic meters per second. At the inlet, the turbulent quantities you would like to set, for example, based on the turbulent intensity and hydraulic diameter. So turbulent energy intensity 5% is okay for internal flows. Hydraulic diameter we already know is 74 centimeters. So it's hydraulic diameter of the inlet pipe, which is in this case I think 0.4, and the reference velocity I think it's something like 30 meters per second for this particle for the design point. So let's set this, and at the outlet you can set fixed pressure or fixed mean pressure. So I will set fixed mean pressure, which holds the constant value, but the distribution depends on the flow pattern on the outlet. On the walls, we will use standard wall functions on all parts, which is the default. Interface conditions, we will use the arbitrary mesh interface, which is the default. And the initial condition, we can take the values from the inlet values. And for example, sometimes the solver doesn't like to start from the zero velocity. So usually I set some reasonable direction of the flow, for example. So flow inlet is in Y axis and outlet is, for example, in -x. So let's say it's to give it something reasonable here. And in the post-processing, you can adjust report to your needs. So you can set your favorite units. You can add some additional data directly for comparison inside the report. You can set the blade-to-blade views and meridional averages to be automatically visualized by simply clicking here which part you would like to unwrap for the blade-to-blade view and which part defines hub shrouds and so on. So, but I don't, it takes few minutes, and here during the webinar every minute is worth fortune, so I don't want to visualize anything, but it's very easy to define. Okay, so I was lucky for the TMesh, so I hope I will be also lucky for the TCFD if I set everything properly. Anytime you can click this check button, which will give you if some topologically everything is correct. And now, so keep me fingers crossed again, and I will try to run the CFD simulation and see if I set all the parameters properly, and I will get some physical and meaningful results or efficiency values, for example. Okay, here, for example, you can list, you can watch what is happening during the simulation. So this is the output from the solvers, or these are just the output messages. So it will just tell you which step is running now. Here we can see the residuals, but you can open any line chart view. So here line chart view you can open, and you can here under this TCFD item, we can activate, for example, the quantities, in which here in the display, so automatically it will show you mass flow rate at the inlet and the outlet, but you can get rid of it, and you can, for example, visualize, let's say, the efficiency. So you need to just find the efficiency here. So efficiency graphs, which looks very nice. So probably I set everything correctly. Here in the view, for example, you can zoom these graphs. So you can get here for the left axis custom range. So I can zoom to the, say, range in which the efficiency is. And here you can follow the instant value of the efficiency, which is the orange one, and the average one. And in this way, you can follow the running simulation. All right. So what I would like to show you here, yeah, anytime, for example, you can view the current time step, so you can see what is happening at the current simulation time. So I can click here, view current time step, for example. It will automatically load the data here. It will also appear in the pipeline browser here. So it's time or iteration 225, and you can watch if all quantities are okay, or if something is oscillating or not. So you can, everything seems to be okay at this point. So I can delete it and see what is happening. Okay, so this is it. So let's say, okay, the simulation is converged. So I can click here, skip points. It means it will skip the rest of the iteration, and the result will be taken as a final result. But definitely it would need more iteration to converge, because usually you would like to see, or you want to see, the constant value both for efficiency and average, so to lie over each other. And this points you that the simulation is converged. Yeah, the residuals looks very fine, so everything is okay. So let's say the simulation is converged. So I will click skip point, and now we can, or the TCAE takes these results as converge, and it will create for us the report and so on. And meanwhile, if I'm able to do that before the before the report is generated, let's show how to set, for example, the optimization. So the optimization I can set only if I am really sure about the CFD results, about the mesh, if I get the proper results I want to get for the particular design. And then, okay, if I'm really sure with the setup, with the results, I can go for the optimization. Otherwise, if I'm not sure with the CFD result and then start to optimizing, so it doesn't make any sense. So first you need to master these setup parts, and then you can go for the optimization if you are really sure with the results. Basically, at the end of any simulation, it holds both for CFD, FEA, or optimization loop. You will get something like this report, in which you can follow the characteristics and properties and variables of your design under the current conditions. So let's say here, for example, if it will be converged, the efficiency will be, for example, 68%, 68% for this design. All right, so let's try to quickly set the optimization part. So I will just tell the main, let's say the main topics and main part of the setup. So here I can set the optimization. Oh, sorry, I need to go for TOpt. So here in the general, so operation mode, DOE or optimize. So DOE is just an explicit parametric space, which I define somehow. For example, yeah, ranges for each parameter and so on. Or to optimize, basically at the beginning, there is a DOE, and then we can internally, we have implemented these two algorithms, direct or golden section search. You can also use the external for example, for connecting to the external optimization tools like Dakota or whatever. Then custom initialization script, because we would like to connect to external program, so we need to have the initialization script which connects the TOpt with the external tool. So for this purpose, I would need to take the here the scripts, so initialization script. So I will take this folder and I will put into my working folder here. And basically the initialization script, I think we have no time to discuss it into the detail. Basically it takes the parameters from the TOpt and it will modify the input file for the CAD generation or for the CAD or for the parametric model, adjust the values and basically run the external tool, the CAD tool, which generates for us the STLs for each optimization loop. So basically it where I am here. So this is the script, input script for the CAD model. Here is the variation of parameters and the particular values, and the script based on what you define. For example, takes the blade radius and change this value based on the actual optimization run or DOE run, and so on. So we need to put it in this script. So I will apply this initialization script. Here maximum run. So I think in the original analysis we have 300 runs for this fun. Then here you can put any number of any parameterization, any number of parameters used for parameterization. So here you can use the internal keywords. For example, if you would like to somehow optimize RPMs or whatever, or you can use the custom one. So now let's say I will define just one of them. So for example, one of the optimization parameters for this design is, for example, number of blades, so which is defined in this way, number of blades. So which in this case it should correspond to these numbers. So it will then automatically take this number of blades and will set the proper number of it. The data type is integer. Yeah, linear space, and the range could be what you need, for example, from 5 to 15. And for DOE, we would like to use just 2 samples with the minimum and maximum values, which is set automatically. Then you can also add other parameters, but for the sake of time saving, I will just set 1. Then the track quantities, so which quantities you would like to evaluate and compare for each design. So here I can take, for example, the built-in quantities, which is evaluated by the TCAE, and I can take, for example, the efficiency. The accept range is from 0 to 1, and the optimization function, I will name it as the same. It will be just the efficiency, and I would like to optimize for the maximum. Here's the relative tolerance for relative tolerance where to stop the optimization. So if the efficiency doesn't change more than about this tolerance value or about this absolute tolerance, so let's say here, for example, 0.1% or maybe 0.05%, then the optimization loop will be stopped. And that's basically all. The bottleneck is, of course, to create this initialization script, but it depends on the input, it depends on the CAD. So then usually our customer discuss with us, and together we create this initialization script. Okay, so now let me save it, and basically now you run everything and the optimization loop will start, but we have no time to do that, to see the results, right? But basically you run it and then you will see. I think I have some example of the report here. I think it was one part of some our previous webinars for the older version. So basically maybe I will find it here. Oh yes. So here are the results, TOP report, and here is the report. Again, HTML report in which you will see all the parametric variations which has been simulated. And at the end, you will see the progress, for example, efficiency for each parameter design. You will find the best point. So 81% was for this parameter variation, and you can check what is the connection or somehow how each parameter depends on the other one. You can see it here and analyze the optimization. And maybe to really to have the full overview of all models, so I will quickly set up what is needed for the FEA analysis. So if I can enable the FEA analysis, and before in the TMesh, I would need the CFD and FEA mesh. And here in the FEA mesh, the setup is much simpler. So here in the STL geometry, you will select the STL of the solid of the impeller, which is also ready from our CAD tool, which is somewhere here. So impeller solid here, perfect. We can visualize it. So if I put here CFD mesh, okay, maybe I need to save it first. Okay, I can see it here. So let's finish this part. So FEA, this is the parameters for the tetrahedra, triangular tetrahedra meshing. So I think the thickness of the solid is something like 0.5 centimeter. So I will set to this, and the minimum, for example, to 1 centimeter, 0.5 centimeter. I said so 1, and for example, the minimum will be 5 millimeters, something like that. Again, and then you have some other options to set, but usually we keep it as default for this meshing tool, and that's all basically. And in the TOPT, when you have nice solid mesh, then you can go for the FEA analysis. So here we would like to do the fluid structure interaction. So here you choose which patches should be mapped on the solid impeller solid. So definitely each part which belongs to the impeller. So I will take all impellers and also the part which belongs to the spiral component. I would like to also include the physical rotation. So I would like to rotate the solid with the rotation I define in the CFD module. I would like to map forces, and as I say, I would like to use the averaged forces which are computed from the averaged pressure on the surface. We can include also the model analysis, which gives us the eigenfrequencies about our design under the given load. here in the solver again, we can parallelize it, so we can set 10 number of processor. You can also choose the preferred linear algebra, finite element or order, first or second. You can use nonlinear equations for larger deformations, stress error estimator. Two of them are here. In the materials, you can put the materials. In this version, you can also, the material can be composed from more, or if your solid part is connected with two different solids, for example, you can set them here. So two different parts can be connected now. Zero displacement region. So you can set the zero displacement for the FEA mesh. I don't know why. Maybe I did something wrong in a hurry, but basically here in the FEA, here in the boundary condition, you would like to set which part is fixed. So usually the shaft or the impeller is fixed to the shaft, so you can create the cylinder which follows the shaft part, which is here, I think, in the Y direction, and set it in the proper way. So all the points in the solid which will be intersected by this shape will be fixed for the FEA analysis. If there is also the heat with the heat application, you can also set the temperature region, etc. And again, for the report, you can set your preferred units, for example. And that's all basically. Then you run everything, you save it, run everything. You can also, FEA can be also incorporated into the optimization loop, and etc. etc. So I think I already said everything I want to say. I already said. So I think it's time to go back to Lubos to finish this webinar and go for your questions.
Exactly.
Lubos, are you still there?
Yes.
I was
yes.
a little bit longer.
No, it's perfect. It was great, actually. So, Radek, thank you very much for this. It was, I know how difficult it is to not to forget about a lot of things.
Yeah,
and
thank you.
yeah, and as the audience know, it's impossible to mention everything, right? There are so many details, but the good news is that once you get familiar with this, it's you do everything automatically, and what's the most important, you have it, you set it once, and then you just replace geometries. You have one settings, and you do it just once, right? So you do not need to set this all the time, right? You do it once. Most of the time you use the default settings, so it's maybe much easier than it looks in the for the first site in the beginning, but that's life, right? You know, nobody knows how to ride a bike for the first time, but for in the future it's much easier. Okay, so it's definitely time to move in the webinar. So thank you, Radek, for this part. It was really great. I like it so much. And now it's time to ask questions. So I would like to ask the audience to ask your questions. Use your time to the fullest. It's your time. So we'll do our best to answer it. Because as mentioned, it's impossible to mention everything. So we are ready to answer also the details, and we will pick the representative questions and answer them right now. We already have a couple of questions. So the question which comes relatively often, so we should take more care and explain this more clearly. So the design is not part of this, right? So TCAE is primarily a simulation tool, right? Where the design, the model, the CAD model has to be imposed into it. But we have in the past, we have seen so many workflows, so many working workflows, and so many geometry builders. So we call them geometry builders, which is a software which creates the geometry. So we can advise. So if you have some idea or tell us what shape is your data, and we'll be, I guess, we'll be able to help you to advise you what to do to get the geometry or even parametric geometry to be able to run these optimization loops, etc., etc. So yeah, so TCAE is primarily a simulation tool, but we've seen a lot, so I'm sure we'll be able to help. Okay. Jesus is asking if we can run multi-phase. I would say not very much. TCAE there are ways how to tweak it, but we don't recommend to use TCAE for multi-phase simulations, because we believe that multi-phase is specific, and there's a lot of modeling and a lot of uncertainty as well, and so we recommend to, if of course if it's possible, we recommend to stick with single phase where we know we're accurate, it's benchmarked and tested and everything, and multi-phase is very very big topic, another topic I would say. Joanna is asking if we can create surrogate models for optimization section. We're working on it. It's not presented in the current stable version, but we are working on it definitely. We see a big future in as I mentioned earlier in the webinar, in less simulations and more, let's say, like design and data analysis. But of course, simulation will be always here. It will be always needed because it tells us the theoretical states of the model. So we will, and the new module is on the way. It will certainly take time because we need to create proper databases to allow our users to create his or her own databases, and then use machine learning algorithm on it. It's on the way. Okay, the next question. Harald is asking about, again, comparison to OpenFOAM. Well, OpenFOAM is a wheel, but people want cars, right? So actually, people want to get from place A to place B, and OpenFOAM is wheels. If you, we don't compete with OpenFOAM because it's something which is absolutely incomparable. Yeah. So Radek, can you see some appropriate or representative questions we would answer?
Maybe I quickly see one. What other typology of centrifugal pump can be modeled with the software package? So with TCA and with the simulation tool, all types. So all the types for which you have the geometry and follows some rules to be able to create a domain for them, pick up what is rotating, what's not, which basically are, I would say, 99.9 centrifugal pumps. Maybe all of them can be modeled. But the question maybe was to TCAT, which was designed for this particular topology, right? So if you have the STLs for any centrifugal pump, you can simulate with it within this package.
Yep. Yeah.
And the STL files ourselves, yes, right. So there is no CAT incorporated. So the STLs are basically the inputs for the software. And if you have them, then you can do the whole workflow I've shown.
Yep. Okay. I think, Radek, I think this would be it for today, because I don't see any really good questions worth to answer right here for everyone. So I think this would be it's time to move on in the webinar. So I just mentioned that here are a couple of those who already share our visions with us and use our software, and this will be it. So do we say hello, Radek? Or bye?
Yeah, I just would like to thank you to all who's watching this webinar, and I would like to say that we are we are open to your questions, to your problems, for solving your particular projects. So we are here for you and looking forward for contacting us. So thank you and have a nice day.
Okay, yeah. Thank you for me. Thank you for your attention, and let us know how we can help. It's our job and also a pleasure. So let us know, and let's see what we can do together. So thank you for watching us, and bye bye for now.
Bye bye.